Hi, my name is Phil Ferriere, and I'm here to give you a detailed review of my data mining capstone project, part of the Coursera Data Mining Specialization, offered by the University of Illinois at Urbana-Champaign. The purpose of this video is to go over the 6 data mining problems we were asked to solve. For each of them, I'll discuss the techniques I experimented with, my results, and how they can be generalized either to solve related problems or work with similar datasets. All data mining tasks were performed on a subset of the Yelp academic dataset. The original data contained 1.1 million reviews for 42,000 businesses, but out of these, we only worked with the restaurant reviews. The 6 tasks shared common processing operations that always had to be applied on the text of the reviews. To avoid repetitions, I've decided to discuss them in this one slide, and as I go over each task, I'll mention what additional steps had to be implemented. For this capstone project, I used the R programming language and the RStudio IDE. Only once did I have to switch to C++ with a Google library called Word2Vec, but we'll talk about it later. In order to analyze the text of the reviews, I always started by building a corpus of the dataset of interest. A corpus is just another name for a collection of documents. The corpus was created and processed using the TMR package. I applied several text transformations, including changing letters to lowercase, removing punctuation, numbers, and extra white spaces, eliminating stop words are the most common words of the English language, like a and the, and finally, I also applied stemming, meaning I only worked with word radicals. Term frequencies were collected with TM either by building a term document matrix, a TDM, from the corpus, or its transpose, a document term matrix, or DTM. In a term document matrix, each row stands for a word, each column for a document, and each entry in the matrix is the number of occurrences of the word in the document, or a weighted version of it. When generating TDM or DTM matrices, 2 different weighting functions were typically used, either term frequency weighting, TF, or term frequency and inverse document frequency weighting, TF-IDF. For the first assignment, the goal was to extract the major topics in restaurant reviews and come up with a visualization to assess the differences in topics between positive and negative reviews. For this, I tried 4 different topic modeling techniques. A topic model describes a document or documents as being about a set of topics that appear in different proportions. Each topic is described by a set of words that also have a unique distribution. My best model was a latent dirichlet allocation model, or LDA, fitted with Gibbs sampling. By best, I mean that subjectively, it was the model that generated the most meaningful set of topics. These topics could be grouped into 3 broad categories: type of cooking or food served, quality of service, and type of venue. How did that list of categories change with the type of review? It didn't. Applying the same model to all the reviews, only the positive ones, or just the negative ones, I ended with the same broad categories. But the word distribution describing each topic did change. To visualize these changes, I decided to experiment with word clouds. Typically, word clouds are used to capture term frequencies, and the more common a word is, the bigger the size of the font used to display it within the word cloud. Here, I used intra-topic ranking instead. What I mean by that is that I used a word distribution that describes the topic, and gave the top term a weight of 20, and the least common one a weight of 1. Then, I paired the topics between negative and positive reviews, and display the word clouds side by side. In the example shown here, the green word cloud on the left is for positive reviews, while the red one on the right comes from negative reviews. The topic is the same, and as you would expect, the most common terms are identical, food and service. But you can easily see the differences in appreciation. On the left, you can see the stems for words like amazing or excellent, friendly. On the right, what you see is a lot of negative words like horrible, terrible, and bad. To use the same technique with your own dataset, first extract topics, and once you've paired them across positive and negative reviews, look at how the word distribution of each topic changes. For a consumer electronic product review, the main topics may be about packaging, durability, or ease of use, what is good or bad about each. Any business interested in understanding what customers like or dislike about their brand or products can benefit greatly from this improved level of detail. The objectives of the second assignment were to identify the best way to represent a type of cuisine using review text data, find the best way to compute and visualize similarities between two cuisines, and finally, select the best technique for clustering cuisines. For task 2, I did not build a topic model. Instead, I used term frequencies with TF-IDF weighting. It was much faster than topic modeling and gave me very good results. To be fair, the quality of the clusters generated depended more on the choice of similarity measure and the starting number of clusters than the text model used. To compute similarities between cuisines, I decided to use the cosine distance as a baseline and then experimented with 3 measures of correlation, namely Pearson, Kendall, and Spearman coefficients. In the end, I decided to use Spearman coefficients because in the last part of this assignment, they yielded more meaningful results when clustering cuisines. To visualize similarities, I use correlograms. Every cell in a correlogram represents the similarity of 2 cuisines. One only needs to follow the horizontal and vertical lines leading to that cell to identify which 2 cuisines it is comparing. The deeper the color, the stronger the similarity of the 2 cuisines. Correlograms are sometimes represented as a full matrix, but here I'm only showing the upper triangle of that matrix because the lower triangle is a mirror of the upper triangle. Instead of showing the similarity value for Japanese restaurants and sushi bars, it shows the similarity between sushi bars and Japanese restaurants, which is obviously the same. For the last part of this assignment, I evaluated 4 hierarchical clustering methodologies using link-based similarity. I also tried 3 different numbers of clusters. The most meaningful clustering was obtained with average link hierarchical clustering and 9 clusters. In the final correlogram shown on this slide, the clusters are marked as black squares. The image on the right is a zoomed version of the bottom right cluster in the correlogram. As you can see, all 9 styles of Asian cuisine were correctly grouped into the same cluster. With fewer clusters, 7 instead of 9, cuisines that you would not think of associating together ended up being grouped. Indian cuisine and Indian buffets were merged with Asian cuisines, for instance. With more clusters, cuisines that should have been together ended up in different clusters. That's why, for this dataset, I settled on 9 clusters. Here again, you can use this with your own dataset. For any online retailer that sells hundreds of thousands of products, being able to group products in meaningful categories is required to help online shoppers. It can be done from customer reviews, as we saw, but also from product descriptions. By varying the number of clusters, or clustering within clusters, you can also identify subcategories within categories. However, to really benefit from the type of hierarchical clustering I used here, you need to be prepared to experiment with different kinds of clustering algorithms and different similarity measures. You'll also need to spend a bit of time fine-tuning for the best number of clusters. On the 3rd week of the project, we were given a list of dish names. Armed with this list of seed terms, we were to mine additional dish names from restaurant reviews. For this task, I decided to experiment with a different vector space called Word2Vec. Word2Vec was developed by Google. Its input is a text corpus, and its output is a set of feature vectors for the words in that corpus. Features such as the context of individual words. The purpose and usefulness of Word2Vec here is to group the terms with similar context together in vector space. The original list of dish names I used as seeds were for Chinese cuisine dishes. I encoded these n-grams into Word2Vec vectors and searched the encoded corpus of Chinese restaurant reviews for terms that were close to the original list, as measured with the cosine distance in Word2Vec vector space. The only technical challenge here was a minor one. It was mostly about integration. The code that Google has published for Word2Vec is in C++. There are a couple of R packages that support Word2Vec, but that didn't really work for me. So I had to hack a little bit around importing and exporting vector space representations between my R code and the Google C++ tools. I also had to run word-to-phrase first because many of the dishes were bigrams and trigrams. It was no big deal, and it turned out to be really worth it. Used in positive space, cosine similarity is between 0 and 1. To mine additional dishes, I only kept n-grams that had a cosine similarity above 0.85. That gave me quite a few additional Chinese dishes. It also gave me a lot of terms that were cooking terms and ingredients, but it's not that surprising. With popular dishes named fried rice or sautéed green beans, other cooking terms are bound to be matched to them. Snap peas can be both an ingredient and an appetizer. What was a bit more surprising was that it also matched dishes from other cuisines, like pollo diablo and chocolate mousse, even though I was only using the corpus of Chinese restaurant reviews. Although it was beyond the scope of this assignment, those could be filtered out using exclusion lists or set intersections. I would expect pollo diablo to be more frequent in Mexican cuisine and chocolate mousse more common in French cuisine. That's information we could use to force membership of a dish in a cuisine where the n-gram appears most often. To use this with your own dataset, the process is fairly simple. First, build a list of terms to be used as seeds. Second, encode them and your corpus in a word-to-vec vector space. Third, use a similarity measure to mine terms similar to the ones present in your master list. You can use those new terms to suggest related or additional products or services to the ones customers are already searching for on your website. You can also use those terms to improve search results by including hits for the additional terms as well, not just the ones the user typed. Linking terms, concepts, products, information is always a great way to promote surfing on your website. Tasks 4 and 5 were tackled together. Task 4 was about finding the best way to rank the dishes of a particular cuisine based on the reviews that mention those dishes. Task 5 was about ranking the restaurants that serve a specific dish based on the reviews that mention that dish. To rank popular dishes, I tried 4 different approaches. I tried ranking a dish by term count, measured over the entire dictionary of reviews, by the number of reviews mentioning a dish, by the number of restaurants whose reviews mention a dish, and finally by sentiment, using a function of the ratio of positive over negative sentences about a dish. To compare and visualize the differences between the 4 ranking models, I experimented with slope graphs. Slope graphs were introduced by Edward Tafte back in 2002 as a way to compare changes over time for data that can be laid out on an ordinal or interval scale. He provided an example to show cancer survival rates over 5, 10, 15, and 20-year periods, as shown on this slide, for different types of cancer. Here's my first attempt at combining the 4 rankings in one slope graph. Here, dim sum is first by 3 rankings. For these rankings, it appears first and at the top. By restaurant mentions, where it is ranked 18th, you can see a huge dip to 18th position toward the bottom of the graph. So this slope graph certainly captures rank by position and order very well. It also captures similarity between rankings. The first 2 models resulted in almost identical rankings, and that is made visible by the many short parallel slopes between the first 2 vertical axes. It also does a good job at emphasizing major changes in ranking with long, sharp slope lines as we saw for dim sum. That being said, a large number of crossing slope lines can be overwhelming, so I tried a different approach. In this version, slope lines were not allowed to cross. The resulting slope graph is easier to read, but some ranking information has been lost. Dumplings, that we saw rank 18th by restaurant mentions, appear first and at the top on that axis. In the previous slope graph, the large number of parallel lines immediately told us that the first 2 ranking models were almost the same. It's definitely not as obvious here. Also, for what were high slopes before, we can see that their range is very limited now. Going back to the first try, decreasing the number of items to show in one graph, from 20 to 10 for instance, also reduces the crisscrossing of slope lines. Displaying 10 ranked items at a time is typical of how search engine results are presented. But beyond this obvious approach, I really wanted to see if things could be somewhat improved when you must show a large number of entries. Making the graph interactive using a mouse hover to highlight a single ranked item in a different light type and color really improved readability. Also, keep in mind that these slope graphs were generated in R with ggplot2, not the greatest library when it comes to creating visually appealing designs. It is not D3JS. But with just a tiny bit of interactivity, visualizing changes in rank for a single item became very easy. For task 5, where the goal was to recommend a restaurant where you could try a specific dish, I used different ranking models, but overall, I followed the same approach. So I'm going to skip over these slides, which show pretty much the same results. But if you have questions or would like to read more about the specifics of this task, then please get in touch. So when should you use a multi-rank slope graph? Today, whenever you go to your website and want to compare items, listings, rentals, or products, you are presented with a drop-down box with an order by choice. It can be order by price, reviews, top selling, whatever. You then get a ranking in the dimension you selected. If you want to see how items rank according to another dimension, you must go back to that drop-down and get a new set of results. But the results of the previous ranking are no longer available. When you get to your third drop-down choice, good luck remembering how each item fared in the first ranking. This approach really constrains users in making a decision by relying on a single dimension or constantly navigating back and forth between several browser tabs. If you want to allow shoppers to use a more sophisticated decision-making process and you actually have rankings along several dimensions, then combine them in a slope graph, or let the user choose which dimensions to include. Here are a couple example scenarios, and I'm sure you'll think of many more interesting ones than I can. But what if I wanted to compare how my online buddies rated this year's Oscar winners on Netflix, for instance? That information could be combined in a single slope graph, with one vertical ranking axis per friend, and on the left side, the movies that I could move my mouse over. Then individual slopes could be highlighted, brought to the forefront, while the other ones are slightly pushed back toward the background. There are many ways to make this look nice. If I'm an online shopper looking to purchase a new camera, and what matters to me is durability, ease of use, battery life, and customer support, then please let me see how the ranks of the top 10 sellers change in all dimensions. To use this with your own dataset, you can actually start with the rankings available in your current order by dropdown. Build a nice visualization with D3, not ggplot2, and combine rankings together. It works for both qualitative and quantitative rankings. If you show many items in the slope graph, make sure you have a unique rank for each in all dimensions. If you don't, you will need to find a way to separate ties, for instance. When I built the slope graph for restaurants, several had the same rating, the same number of stars. But by recomputing the average of the reviews myself, I could differentiate between two 5-star restaurants because their scores really were 4.72 and 4.87. It's not really a showstopper, but that's something you need to be aware of and plan a workaround for. For our last assignment, we were asked to train a classifier that could predict if restaurants would pass a public health inspection based on their Yelp reviews, as well as some additional information, such as type of cuisine, star rating, number of reviews, and restaurant location. In order to start with a sound baseline, I decided to train two separate classifiers, one that only used the additional information and no text features, and one that used both, just so it would be easier for me to assess by how much the text features improved the predictions. I tried different text feature representations, using combinations of unigram and bigram models at different DTM sparseness. Sparseness here really defines the size of the document term matrix. At a sparseness of 0.85, the DTM only contains terms whose proportion of zero counts is less than 85%. It allowed me to work with only a few hundreds of text features, not tens of thousands. The final model, with text features, was a combination of TF-FDF-weighted unigrams and TF-weighted bigrams. To train classifiers on comparable features, whatever their type, one hard-encoded zip codes, frequency statistics, I perform z-score normalization by subtracting the mean of each feature and dividing the result by the standard deviation from the mean. And I also discarded low entropy features, that is, predictors with constant values or near zero variance. I split the original label data into 80% training and 20% testing partitions, and made sure to keep the original stratification for the outcome values. I did not need to create a separate validation set because I wanted to use 10-fold cross-validation on the training set, meaning that for each fold, 10% of the training data was set aside for validation purposes. To train and hypertune the classifiers, I used the Carrot-R package. It's a great package that provides a wrapper with a consistent interface around many different kinds of classifiers. By default, Carrot uses accuracy and kappa to evaluate classification performance. But there was a major imbalance between positive and negative outcomes in the data. And it makes sense because many restaurants pass the half inspection while only a few fail. If I trained a classifier to always predict that a restaurant would pass the inspection, no matter what the input data, I would have a highly biased classifier with a very high accuracy, even though I wasn't doing any real classification at all. So to assess performance in a more meaningful way, and to provide a different training objective to Carrot, I computed the EF1 score instead, that is the harmonic mean of precision and recall. I trained 7 different classifiers, including XGBoost, GBM, KNN, SVM, random forests, and 2 naive-based classifiers. Without using any text features, support vector machines, random forests, and stochastic gradient boosting showed very similar F1 scores. The single best classifier was a naive-based classifier, but the great value of doing 10-fold cross-validation repeated 3 times is that it allowed me to identify which classifier's performance was more consistent. Looking at the estimate of the out-of-sample error by measuring the performance of the tuned classifiers on the test set, again, the top 3 classifiers had very similar results, but because on average it repeatedly performed slightly better, I chose support vector machines as the baseline classifier. Using text features, the random forest classifier was the best, but the improvement in F1 score over the non-text features SVM classifier was only marginally better. To understand why, let's look at variable importance. Random forests, backtrees, boosted trees all have built-in mechanisms to provide that information. Support vector machines don't. But one of the great things about the Carrot package is that it still provides it by doing an ROC curve analysis for each predictor. According to the variable importance table on the left, the one for the SVM classifier, restaurants that failed the health inspection tests are characterized by a high number of reviews, and the type of cuisine they serve, mainly Asian cuisine. They are also mainly located in 3 specific zip codes. Now, if you look at the variable importance table for the random forest classifier using text features, the top predictor for a restaurant failing the inspection test is the presence of the word noodles in the reviews. Does it mean those restaurants serve somewhat contaminated noodles? I don't think so. If you look closely at the table, you can see again that the restaurants are located in 3 main areas, the same zip codes as the ones on the left. Chinese restaurants are again at the top, but Thai, Vietnamese, and Japanese restaurants have disappeared from the list. Well, not really. They've been replaced. The term noodles here is a substitute for the Thai, Vietnamese, and Japanese restaurants where they are one of the most popular dishes. And that's what the random forest classifier, trained with text features, brilliantly captured. Adding text features can help make your model more accurate and increase its interpretability, but the quality of the results varies with the dimension of the vector space you use. When working with term frequencies in a DTM, results vary based on the sparseness of the DTM. When working with topic models, results are affected by the number of topics chosen and the number of terms used to represent each topic. So it might make sense to modify the hypertuning process to do a greater random search for the right vector space size at the same time as you're tuning the classifier's hyperparameters. That's it. If you would like to learn more about me or my work, please don't hesitate to reach out on LinkedIn or via email. If you're a student who just enrolled in the data mining specialization and would like to know more about my experience with the Capstone, feel free to send me your questions, and good luck to you. Thank you for watching.